So again, thank you for being here today. I hope your day is,
Not Monday.
Oh, Monday is,
I'm not coming.
oh yeah, no, I'm not going to be here either.
Yeah.
I'm going fishing, okay. Literally. Wednesday, okay. Man, that's not good. Too many lectures being lost. Okay, anyway, where was I? So thank you again for being here today. I hope your day is okay. I hope it's actually great, but I'm not going to patronize you by saying I hope it's great. It is. I hope it's at least okay for you. Let's finish the discussion for interrupts and talk about the UART interrupts. Last time we discussed about how you can configure the UART to ask for interrupts. We started discussing that, but we haven't finished that discussion. We're writing a piece of code. Just that we're all on the same page, let me remind you what interrupts are. Your processor is executing instructions. You have any arbitrary program, you're executing instructions. At some point, a device, through a physical wire, typically, goes and requests an interrupt. So an IRQ request comes from the device. This is done at the physical level. The CPU finishes executing the current instruction, stops execution, saves the return address, PC+4. Remember, we had a very long discussion in a special register called EA, not special, one of the registers which is reserved for that purpose. So here the CPU is going to do EA equals PC+4, right? Where PC is this instruction, the interrupted one, the one that wasn't allowed to execute. It does CTL1 equals CTL0, and then CTL0 bit 0 equals 0. This means disable interrupts. And then PC equals 0x20. Start executing a piece of code. That's the interrupt handler. The interrupt handler is supposed to go to find out why it got called, because there may be many reasons why it got called. There are a lot of IRQ lines, and it might be that even for a single IRQ line, you have many devices connected to it. For the time being, you can assume there is a one device per IRQ, but you can connect many to those. It has to handle that. That's the role of a device driver, right? It has to go and talk to the device, do specific things, handle the interrupt, and then return to the code. And we say, so interrupt executes, this is the interrupt handler now. And at the end, we do EA equals EA minus 4 and UART. And what UART does, it does CTL0 equals CTL1 and PC equals EA. That's what it does. Any questions about this? Yes, please. Because because the machine disables interrupts automatically. So this thing, it requires a lot more discussion to really appreciate why this is happening. What it does, it saves the previous state of CTL0 into a register. This is equivalent to doing a call. When you do a call, you save your return address into a register so that you can make the call. It's an optimization kind of thing. CTL0, as it stands, the only thing we know, there is a bit at the end which is interrupts enabled. Right? So this just makes a copy of that bit. The reality is that CTL0, if you read the manual for NEOS, you'll see it has a lot of other status things that say control the behavior of NEOS. All this thing it does, it makes a copy of whatever the status is, which you don't know, and changes it automatically to disable interrupts. It leaves everything unchanged, everything else. All the other stuff we don't know about. It's basically a mechanism to allow you to safely disable interrupts without having to worry about it. And it gets involved also if you want to do nested interrupts. So far we haven't talked about nested interrupts. What if you want to enable interrupts within the interrupt handler? That would be a scenario where you have a device you don't care that much, like I don't know what might be, like moving your mouse is not as critical as maybe playing a particular audio sample at particular time so that you listen, or the other way around. Anyway, I'm mumbling. So we finished the discussion about the UART. I want to remind you, we had two pieces of code that we were writing. Our memory looked like this. There is the interrupt handler, which is a location 20. This was text. Then we had our code, our own code. This was an infinite loop that just prints out characters on the screen, and on your UART sends characters. And then somewhere in memory we had the character, which initially was initialized to 0. Okay, everybody okay with this? You remember that? Okay. we wrote everything. There was a point where we said there's a dot data section, and there is that car, and dot byte. In the beginning, we had this as space, which is the number 32, by the way. Okay? And then we had the code that was writing, doing the infinite loop, and the handler. I'm not going to rewrite the handler. I'm not going to rewrite the main code. All I want to do right now is configure the machine so that the UART will request interrupts anytime a character is received, and the CPU will accept those. That's to do that. So we're going back to our main code, .text. And I think we're writing like the fever code, forever doing something like that. And all I'm going to do is I'm going to write a bunch of constants to specific registers and memory locations that correspond to configuration handles for the device and the CPU. Just to remind you, there are two things we got to do. We got to make the UART ask for interrupts, and we got to make the CPU listen to those. There are two different things. So first thing we got to do is we got to say to the UART, ask for interrupts. This is the point where you helped me last time and you remind me how the registers are, because I had the page over there and I wasn't looking at that. Hopefully I gathered that page, and I cannot find it today again.
Bit 1.
Huh?
Bit 1.
Okay, bit 1. Yes. So there's for the UART, the one we're talking about, there's the control status register, which is at offset +4 from location 0xF201000. So it's a 1004. There's a register there. And there are 2 bits that we care about. These are not indicator bits. These are switches. So you can read them, but they're really meant to be written to. And this is the enable receiver interrupts. And this is the enable transmit interrupts. So I think R stands for read and the other stands for write, but you have to interpret this receive and transmit. Okay? These are initially, when the system powers up, zeros, which means that UART is going to silently keep, it's going to keep in silence and not bug you at all. If you want it to ask for interrupts, you got to go and write 1 on this location. What the UART will do is anytime it has space, anytime a character is received from the outside channel, whatever the channel is going to notify the CPU. Right? So what it's going to do physically is going to go to line 8 of the IRQs, IRQ 8, and it's going to erase it to 1. I think it's 1 means please listen to me. And it's going to keep it there until the CPU goes and reads the character. Okay? All right with this? This is important to understand. The device is dumb. That it says it doesn't just knock on the door once and then waits until you open the door. Don't use that analogy. It's basically on the door and like knocking all the time until you open. That's the idea. It's like open now, open now, open now, open now. I keep saying that. That's very important because you got to handle that. And you have to be careful whether you need to enable interrupts in the middle or not. So to do this, we're going to do the following. Get a pointer to the device. And then we got to write a constant to it. What is the constant? The constant is the value 1. What we care about is to write something there such that the first bit is 1. And you cannot use, no, actually what I said is the following. You want this piece to 1 and this to be 0. Right? So this is the requirement. You don't want to set this as 1 as well, because then it will tell you, oh, I cannot send the character if you have 1. We don't want that. So we're going to do also a movie, R9, 1. The important thing is this has 1 at the bit 0 and 0 at the bit 1. And then we can do a store word IO, R9, 4, R8. Now, from this point on, if you had a way of probing, if you could had a way to look at wire 8, IRQ 8, you will see it going up anytime a character is received and staying there. Okay? In our system, unfortunately, that's not possible because the device and the CPU are inside the same chip. So you got to rip it apart and somehow manage to get a problem there. Forget it. It's not happening. Okay.
That would only enable read.
Interrupts, exactly. So anytime somebody from outside sends a character and the receiver gets it, it notifies the CPU and starts saying, I have a character, I have a character. Now, the way to understand that is there is an IRQ line, IRQ 8, sorry. NEOS is here, right, the CPU. in between those, there are two registers. This is CTL, which one was 3? Sorry, CTL0, and then CTL3. CTL3 is a per line guardian, right? It's the first boss you have to go through. So there is a bit here. It's like, think of a corridor. Either the door is open or it's closed. We want to open the door so the request can go through. And finally, there is the final boss, which is a position 0, which is any request has to go through that final boss. Okay? So we've got to write two things to those registers, set them up accordingly. Okay, so for that, there is a specialized instruction because we're no longer referring to the regular registers R9 or whatever, so there are specific opcodes. And let me find those out so I give you the right syntax. So there is an instruction called write CTL. This means write control register. So it refers to a different namespace than the regular registers, R1, R2, R3. These are different registers. And you write the register you want and the constant you want. Okay. So over here, we have to put a movie, R2, and enable interrupts on line 8. Okay. So if this is line 8, we have 1, 2, 3, 4, 1, 2, 3, 4, 8. Okay. So we want something that looks like this. Okay. So it's one hexadecimal digit, another hexadecimal digit, and another one. The zeros are implied here, so it's fair enough. That's how I got this. And hopefully I know what I'm talking about and that's the right number. If it's not, fix it. So what we've done here is we set this bit to 1, where this is bit, the bit that corresponds to IRQ 8. Again, why is it IRQ 8? Because somebody decided so. That's nothing to it.
WRCTL, is it the assembler or is it a compiler?
It's an instruction. It's like add, branch. It is a special instruction. So if you were to look at the opcode itself, there's going to be a 5-bit, like a 5-bit field that refers to regular registers, and there's going to be another field. I don't remember how long that is. I think it's also 5 bits, but there the number does not refer to the registers. It refers to the control registers. And right now we only know about control 0, control 1, and control 3. But there's a bunch, and every time they build a new generation of the processor, they keep adding control registers because they add functionality to the machine. These are what they are. This is exactly what they are. They're not registers you use for calculations. They're registers that have specific meaning. Specialized meanings. Yes, miss?
So the IRQ8 is at like position 13 on the control 3 thing?
I mean, these are bits I'm writing. So this is 4 bits, another 4 bits, and another one. So it's position 9. Okay. Alrighty then. Now, so we open the first door. Now we have to open the last door, and I hope you understand this is fairly straightforward because we just have to send bit 0 for CTL 0 to 1. We already have that constant here, so we can do a write CTL 0 R9 because it happened to be 1, and that is the main enable. So the moment that instruction executes, interrupts may happen. So the first time that the device may request an interrupt and may actually occur is immediately after this. So you better be prepared to handle it. Everybody okay with this?
Is that last one CTL 0 or 4?
That's my wonderful 9. Basically, it's supposed to be the number 1. I want to set the bit 0 to 1. That's all there is to it. It just happens this code is convenient like that. But you could do it 10 different ways.
So you said after that instruction, you have to be prepared to handle it. That means before all this code runs, you have to do some extra stuff, right?
You have to have the interrupt handler in position.
Okay.
That's it.
So this is just like part of the code that
Yeah.
is executing like directly in your program.
Yes. But of course, in your setup, right, everything gets loaded in memory. And the interrupt handler is there, your program is there, and then it runs. So there's no worries about that.
Okay.
Okay?
Is that order malleable for writing the bit that sets the interrupt for the UART and then the two guardians?
Or you could do it other ways.
Doesn't matter?
Yeah. In this case, because there's only one device, it really doesn't matter. And actually, these two could be flipped too. I haven't seen anything in the manual that says otherwise. I haven't read it very carefully lately to be able to say, to remember whether there is some note in the manual that says, be careful how you do that because there's something inside the machine. So for the time being, I assume this is okay, but maybe we have to take a closer look at what this says inside the manual. I don't see any reason why this should be different. Okay? But as a matter of practice, I will first enable the device and then the CPU, last thing. Okay. Any questions about this?
Thinking, like, if the device is already enabled and it's trying to send stuff before
Yeah,
the CPU.
or you're just ignoring it.
Yeah.
Okay. See, in this case, there is nothing that may happen, but in other cases, I don't know. I don't want to make comments in general because who knows what other devices might do. Any questions up to this point? Okay. Now, the way we wrote the code for the handler last time, we're using registers that we knew were different from the code because we controlled both of them. The reality is if you had a machine out there and you were writing software, chances are you're using libraries, using anything, whatever, and the interrupt may happen at any point. So you cannot assume that the registers that the interrupt handler is going to use are okay to use. This is like a call. However, you don't know the call site. Remember, for regular calls, we have, by agreement, a separation between caller save registers and callee save registers. Why? Because we control the call site. We know where the call happens. So the caller has a chance of saving the things they care about, and the callee then can take advantage of that and use caller save registers if he wishes. You with me on this? Interrupts are like a call. The only difference is you don't control the call site. Call site can be anywhere. Hence, there is no such thing as a caller save register for interrupt handlers. Everything is callee saved. Again, why? Because you don't control the call site. It could be at any arbitrary point in any arbitrary program. So any registers you touch within the interrupt handler have to be saved somewhere, and that somewhere is the stack. That's the way you use it. So, can I erase this? So let's go back in the interrupt handler and let me write a prologue and epilogue where I'm going to pretend to be saving some registers. So remember, we're writing dot section, dot exceptions. I don't remember, is it exception or exceptions? Dot archival and execute. That is, do store data there. And this is going to be execute exceptions. So interrupt handler, not sure you can use two letters, but anyway, let's do that. What do we do? This is, let's say we want to use 4 registers. Let's say we want to use 4, I'm overdoing it, 2 registers. Let's say I want to use R2 and R4. Okay, these are just 2 arbitrary registers, could be any register, right? So what will I do is I will do the following. I will say add I SP minus 8. Why 8? Because there are 2 registers I want to save. Next thing I will do will be store word R2 0SP, store word R4 4SP. Nothing to do with the fact that this is register 4. Just 4SP. Then you can have your regular code. At the end, you mirror those. You say load word R4 4SP, load word R2 0SP, and then we're going to do add I EA minus 4 and ERET. Okay? Yes?
Can this thing fly?
Oh, this thing.
Yeah.
Can I?
Just lift it like this. This is.
It's okay?
Yeah.
Okay, good. Sorry for writing down there. Maybe I should write here. I think that's within the frame. Okay. Everyone okay with this? Now, next thing. What we've done so far is we assume that the only reason why interrupts will happen is any questions about this? Because I see you guys. Now I think I blocked the view for some other people. Any questions about this, or we're okay?
It doesn't matter in which order you do the last two load words, right?
No. Yes?
We don't know what's in R4, right?
Huh?
We don't know what's in R4.
Exactly. Actually, we don't know what's in any register. The only register we know that's useful to us, that's meant for us, is EA, which I think is R29. Just don't take it home. All right.
Put the stack back, take the 8 back off.
Well, maybe. That would be a good idea. Sure, yeah. Just to please you, yeah. And
I made that mistake with the lab, so.
that is called debugging.
Yeah.
But debugging interrupts is horrible because they happen at any point. So, which means you don't know where they're going to happen. And every time you run your program, it may happen somewhere else. So thank you for that. I apologize. As always, I wasn't testing you. Okay, so moving on. So I can screw up something else. Okay, so next thing. So far, we're assuming that the reason the interrupts are happening is because it's the UART. And for our examples, that was the case because we control the machine. We have enabled only the UART. Any point you want to do anything really useful, you're going to find that there are going to be a lot of stuff that you got to control. For example, if you want to do the rollback control, where you have motors, you're going to have pieces of code that run on using a timer. We're going to do the timer next week. Maybe we'll start today. We'll see. You're going to want to send pulses so you can control the speed, who is on, who is off, whatever. And you can do that nicely with interrupts. We're going to see that when we do the next lecture. So there's going to be some channels where you control the motors. There are 2 motors, so maybe 2 of those, 2 devices for that. On top of that, you're going to have sensors, which are the switches. So you may have interrupts for those. You may have many devices. Any PC, any computer system today has a lot of devices. There is your mouse or your touch screen. There is the screen. There is packets coming from the internet, whether that's a modem, wireless modem, or an actual Ethernet card. So many devices that run at the same time, and they all use interrupts, like audio and things like that. So what you need to do in NEOS is the following. Unfortunately, in NEOS, the detection of who is calling is done by software. It has to be done by software. So next thing we got to do, after we save some registers, we have to go and find out who is calling. One way of doing that is to go and start asking. It's like saying, somebody's knocking on my door. I cannot easily come up with with a nice physical analogy of that. You don't know who knocked. You just have to go and keep asking everybody, did you knock, or did you knock, did you knock? It's like you open your door, there's like 15 people in front of you, and they're all sitting like that. And they're not saying anything. You're just looking at them, they're looking at you, so you have to ask, did you knock? And there's no way to broadcast and say who knocked. So you have to go and interrogate them. So again, if you have those notes from last time, if you go to the control and status register for the UART, there were these 2 last bits which were switches. And there are 2 more. I think it's like a bit 8, a bit 9, if I remember correctly. Maybe I'm wrong on this. And one is there is a read interrupt pending, RIP, that's easy to remember. And then a write interrupt pending. This is, you just received a character and you did ask for an interrupt, and that interrupt is enabled, all right? The other is you are free to send a character. So you can go, as part of the code here, go read the control status register and ask the UART, was it you? In our code, of course, this is not needed because we know it's the UART. But if I had multiple devices, I have to do this. The way you do this per device differs. So every device will say on its manual, well, that's how you ask me. Okay? So far, so good? Now, NEOS does provide some convenience to this. There is another control register, control 4, if I remember correctly, CTL4. Control 3 are the switches, right, where you enable interrupts. Control 4 are indicators that say which interrupts are pending right now. So this is a 32-bit register. With 1 bit, this corresponds to IRQ 31. This corresponds to IRQ 0. You can read this register using a read control, the sister of the write control. You can read that register, and then you can look at the bits that are on, These are the IRQ lines that are active. So you can quickly find out with one read who is asking for interrupts, but they can be many. You can then enforce priorities using software. You can say, for example, I would prefer to handle that interrupt first versus another one. Does that make sense? Okay. Now, that is a convenience. It's not a general solution. It cannot do everything for you, because it is possible to have multiple devices connected on the same IRQ. This is called IRQ sharing. You have a wire, you can have, and the wire has to go one if any of many devices request. So it's a big OR gate. You can have many devices using a big OR gate to go and say, I wanted an interrupt, and because you don't have enough IRQ lines, you have to reuse some of them. For NEOs, that's less likely because there are 32. So it's a little bit hard to find 32 devices to plug in there. But systems are getting very complicated these days, and there might be 32. For other systems, you don't have that many. Right? Especially if you have a physical system where this go off a chip and they have to go through a PCB, whatever. These are actual wires, and these are pins are very valuable real estate on a chip. So you may have setting there, so that would not be enough. In that case, you have to resort to and go say, okay, I know it's IRQ X. How many devices are on that? Let's go ask one of them. It's one of them in order. Okay. Questions up to this point? I know I'm mumbling, but there is nothing to write about this stuff. Right? That's what it is. Yes?
I'm confused about the read and write interrupt pending, because how could an interrupt be pending if it's called instantly?
This says, anytime you receive a character, ask for an interrupt. Okay? This says, I am actively asking for one. Okay. Think of a system now where you have 10 devices. One of them is the UART. And you configure all 10 of them to ask for interrupts. You get an interrupt. Who was it? Okay. Don't they call it as who done it? I mean, that's the thing, right? Who is the whatever. Okay. So you go to the interrupt handler. Why you got called? Because at least one of those 10 devices asked for an interrupt. Which one was it? One option is to go to CTL4 and look which ones are on. The other is go to the devices. If you go to the UART, you say, okay, I know I enabled, but are you really asking? Do you have anything?
Oh, is that the CSR specifically for the UART?
Yes, for the UART.
Okay, so that tells you.
This is a UART specific thing. This has nothing to do with other devices. Other devices will have different mechanisms.
And you would check that within the interrupt handler?
Yes. 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 Okay. So far, so good? All right. Next thing. Nested interrupts. Any questions about this? I see you looking at it and saying, okay. All right. Nested interrupts. What is a nested interrupt? So, and the perils of not handling them correctly. That will be the title of the book. All right. So I'm executing some piece of code. This is my program. In the beginning of time, I wasn't executing an interrupt handler. I'm just executing a program. Okay, and I have multiple devices. I get an IRQ, right? Some device says IRQ. And let's call this is device A, right? Some number, okay? I go to the interrupt handler now, and this is the interrupt handler. And I'm executing code. But let's say now somebody else asks for an interrupt. The way we have things set up, remember, the first thing that the hardware does when it does this, induces this call is to disable interrupts. That is, the CPU now is doing this, la 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 la, right, not listening. So this has to finish. You have to go back. You're going to try it maybe to execute one instruction or not, and then you can handle the next interrupt, right? Let's pretend this was something very critical, right? This is, I don't know. Any I can think of doesn't sound nice. Any examples? Like something really critical, somebody's going to die. What can you think?
Falling.
Huh?
An elevator falling and you have to put the brakes.
Okay, that's a good thing. Okay, yeah, sure. So you have elevator music, right, playing with some super duper DAC over there, like 192 kilohertz super sampler, whatever, and you got to play a few notes over there. So you got called the interrupt, you're dealing with the ADC, whatever, and now you're right, the elevator starts falling, you get indication you're going to die, maybe. And the CPU says, oh, I'm sorry, I got to play the music. Anyway, let's
save the CPU.
Yeah, sure. I mean, at least you're going to die in style. Okay, good. And we all love elevator music, of course. So we got to handle that. So it's a more critical interrupt. So a more sane thing to do would be to enable interrupts here. And then if you really think about it, if you view this as a black box, this is some code that's running. Right? Who cares that there was an interrupt in between here? I want to induce another call here. Right? I want to enable interrupts again so I can have an interrupt within another interrupt. If you really think about it, because this is a sequence of instructions being executed, who cares that you were inside the interrupt handler? This is like executing any arbitrary piece of code. I'm just going to invoke it again, but for a different device. So I want to enable interrupts here. In Neos, all of this has to be done by software. Neos by default would disable interrupts to give you enough time to save things and prepare so that if you wish, you can enable interrupts. Okay, so we do this. Let's say we have the UART, and somehow we have something else, some other device like a button where you press, you're going to get interrupts. So let's say I'm doing that over here, and then I say, I want to enable interrupts. Okay, right. So what can I do now? I can do the following. I can say, by the way, here's the thing. If I'm going to enable interrupts, what's going to happen is the moment an interrupt is taken, Neos is going to override CTL0. So and I don't know what the interrupt handler will do for that other device. So another thing I got to do is I got to save CTL1 on the stack. So first thing I will do is instead of having 8 here, I will do 12. If this is not clear why I'm doing that, just follow me for a second and we'll explain it at the end. I don't remember the syntax for CTL. I think it's like this. CTL1 to, let's say, R4, because we just saved R4, it's okay. And then we can do a store word R4 8 SP. And this is the code I'm going to write after that. And over here, we can have a load word. Sorry, there's not enough space. So let me write here. Load word R4 12 SP. Write CTL1 R4. Okay. All I've done for the time is I saved the state of CTL1 on the stack as well, and then restore it at the end. Now, I'm going to write code that goes in here now. And my goal will be to enable interrupts. So far, so good? How can I enable interrupts? Any ideas? Thank you. Movie. We just saved R4, so we're free to use it. Movie R4.1. Write CTL0 R4. So that's a 4 again. From this point on, by the way, there's a lot of code in here, whatever is the interrupt handler. Another interrupt may happen. So I just enable nested interrupts. Everybody okay with this? Now, this code has a problem. I'll explain what the problem is. The moment you run it, and the moment you receive a character, you're dead. What's going to happen is this. You're going to happily execute this because interrupts are disabled. You're going to then enable interrupts. Right? Why did you get into this interrupt handler in the first place? Because the UART received a character, and they raised IRQ8, right? What's the state of IRQ8 at this moment? Still alive, still 1. Why? Because you didn't talk to the UART. The UART is still asking. Right? Yes, you've done all these things, but the UART has no idea what you're doing internally. There was no acknowledgement to the UART, I have your back, I'm going to read the character. So you got to go and handle that. You got to make it stop asking. If you just go and naively enable interrupts again, guess what? IRQ1 is 1. Neos doesn't know it's inside interrupts for all he cares, right? It's just random code. It will take the interrupt. So you're going to have a nice infinite loop, keep writing stuff on the stack until you overwrite everything, your machine is dead. I mean, something's going to happen, who knows? Not what you intended. So in this case, we got to go and disable the interrupt. The only way to do that is by going and reading the character for the UART. For other devices, there is a way to where it says stop, shut up. I'll do it when I can, but I got your back, I'm doing it. Everybody okay with this? So there is, in the notes, you're going to see that before doing this, what I'm doing is I just go and read the character. So there is a before here. I know you're going to love me now. There is a movie A, R40XFF201000, which is the receive buffer, and then load would, let's say, which are the register? R2, 0, R4. The moment you've done that, that's the behavior of the UART. The moment you read from the receive buffer, we're done. And you can handle that. By the way, this is going to also, anyway, I'm not going to go there. I'm going to confuse you. Okay. Everybody okay with this? Only
WRTCL, is that R9?
Sorry?
On the left. Is that R9, bottom line?
No, it's. You know, you've seen those videos online where people do calligraphy stuff?
Then is
I'm not one of those people. Huh?
Is RDCTL also R4? The fourth line on the middle. Yes.
This thing?
Yes.
Clearly it's R4. Yeah, no, all of this is, anyway, yeah, I'm sorry it looks so nice. Everything is R4.
Okay.
That is my 4.
They're all fours.
I have the minimum qualifications to be a medical doctor, right? You cannot read my writing. Okay.
So are these two instructions before or after?
This, yeah, so this is a, so this is piece, first piece, okay? This is second piece. 2, 1, third piece. And fourth piece. Now, to my defense,
Wait, what about that thing on the left?
it's beautiful. Okay.
Got it.
Now, to my defense, there was a set of concepts that I tried to develop so that you can see why they're needed. Other than that, yeah, sorry, I should have rehearsed this. Next thing, a redeeming factor. It's very well written in the notes, right, with very nice Courier font. So typeset over there, so you can read it from the text. I want you to remember the concept. Save the registers you care about. Because you're going to do nested interrupts, you got to save serial1 because it gets overridden automatically anytime you get an interrupt. So save that on the stack. Next thing is, because you're talking to the UART, make the UART stop asking, enable interrupts, do anything else you wish. In this case, who knows what else you want to do. Restore things from the stack. That's what it is. That's the concept.
So 4 and 5 is just restoring from the stack.
Exactly. So if you look at 4 and 5, it's supposed to be a mirror of 1. Okay.
And in between 3 and 4, you can do other stuff too, right?
Exactly. You can write anything you want. This is in case the UART is asking. All right. I think I had enough with the UART and its interrupts. Normally, it would be a good time to talk about the stack attack, but let's start talking about the timer, and we can finish this on, it's Thanksgiving on Monday, so next Wednesday. It's going to be quite at some time. Yes?
So for like in section 1's
Yes.
forward R4 8, like offset 8, and then in the fourth section we have offset 12. Like why are we?
I think that's called Occam's razor. That is the simplest explanation is the right one. It's a typo. Okay?
Thank you.
We're good? Okay. Thanks for pointing that out. Now, one last thing I should mention with interrupts is the following. Remember, when we introduced the stack, we said, here's memory. There is a register inside your CPU, which is also called SP. If you take its value as an address, this is the top of the stack, and anything above that in numerical orders in addresses is within the stack. Anything below that is not part of the stack. Anytime you want to put things on the stack, you decrement SP. Anytime you want to take things from the stack, you increment SP. You remember that? Okay. So when you write code, I hope now you have some additional information why it's never a good idea to access locations that are below the stack pointer in address space, because you have no control of who may write to them. Long story short, you're executing your code, right? At some point, you did an You allocated some space on the stack and you wrote the value 10. And then you say, come on, it's my own program. How about I go to -4 from the stack without changing the stack pointer and write in 20. If this is your own code, you control everything right, and you know whether you're going to overwrite the location, you can go and try to write that. However, if for whatever reason you use interrupts, what may happen is an interrupt may happen. And what's the first thing an interrupt routine will do? It will save some registers on the stack because it has to use some registers. So any location that's just below the stack pointer is free for grabs. It may change at arbitrary points that have nothing to do with your program. It has to do with physical events in your system because you get interrupts. Fair enough? So don't ever use stack locations that are outside the stack because they may get overwritten. Alrighty then. Let's talk about the timer. If you haven't guessed it, the timer is a device that allows you to measure real time. So it gives you a way to measure physical periods of time, and you can control what those are. This is a device that ticks at, if I remember correctly, on the machines we have, is a 50 megahertz, or is it kilohertz? I think it's megahertz. Okay. Again, it's in my notes somewhere. You can look at 50 megahertz. Okay. So it's going to do 50 million ticks per second. Okay, that clock is based on a crystal. It's as good as some, run-of-the-mill clock you can, like watch you can get, digital watch you can get. That's the accuracy of it. But it is real time. Okay. What is it? It's basically a device where you can say, start counting from some number. When you reach 0, let me know. That's what it is. So, you say, count 50 million times. The moment you do 50 million ticks, raise your hand. And the raise your hand could be, stand in your corner, raise your hand. I'll ask you whether your hand is up there. Or you can say, look, when you reach you counted 50 million times, come knock on my door. In the first case, you can do polling. There's going to be a way where you can go to the timer and say, are you done counting? The second case, the timer can come back and say, 50 million ticks are up. Time is up, handle this. So this is a very nice way of dealing with real-time events. You can use this, for example, to create sounds of certain frequency if you want. You can have, if you put the pit, you put a speaker on one of the pit connections, you can have this tick every so often. You can move this up and down. You can create a square wave, which will sound like any frequency you want, up to 50 megahertz, divided this by half, because you got to do up and down. Oh, 50 megahertz, sorry. Everybody okay with this? Of course, we don't hear that frequencies. Oh. Any questions up to this point? So first functionality of the timer is count up to some number and let me know. The other functionality is, count up to that number, let me know, but then start counting again. So it's essentially I'm raising my hand, and I also start counting again, so I can have really periodic signals. I'll explain those. So we have 4 minutes left. Let me give you some idea of how this thing works, and then we can continue this next time. So this guy is at some location in memory. But the important thing is that it has inside 6 registers. Each one of them being 32 bits. The 2 of them are kind of status and control. So at distance +0, you have the status register. And this guy looks like this. In the beginning of time, those 2 bits were 0. This is a read register. You read this register, so you can view those as indicator lights. When both of them are off, the timer is doing nothing. When this is on, it means that the timer is counting, actively counting now. When this is on, the timer has raised its hand. So you told it to count up to some number. It counted up to that, and you reached that, and you haven't given it any attention. So the hand is up, means that that period has elapsed. A distance +4 is the control. And it has a bunch of stuff inside it, sorry. ITO, which stands for interrupt on timeout. These are all single bits, right? This is 0, 1. This is, I'll explain what cont means. And then you have start and stop. Okay. Start and stop. Stop means stop counting. Start means start counting. Okay. How much to count is a different set of registers. But this is what it is. Really commands. You know, it's like you're pressing the button, now start counting. You press the button again, you stop counting. So usually what you're going to do is you're either going to write 1, 0, stop, or you're going to write 0, 1. For fun, you can try to write 1, 1. Who knows what's going to happen? You're not supposed to do that.
What about
This-
0, 0?
Huh?
What about 0, 0?
You can write 0, 0. It's just saying, okay, I'm going to bug you, but I want nothing from you. Just, hi, nothing. What's up? Nothing. Means nothing. Now, cont. Continue. Means what? You're counting up to some number. You're raising your hand, but then you start counting again. This is for real-time events, right? Because what the behavior you want to emulate is this. This is time. You say start. You raise the flag, so timeout here. If you don't put continue there, the timer is going to stop. The CPU will have to handle your whatever needs to happen. There's going to be some time there. And then you can say start again. So this is kind of it's not exactly real time because you have this period which was based on counting up upon some clock, nothing to do with the program executing. After that, you have some amount of time that has to do with the CPU executing a bunch of instructions to handle that event, and then you can start counting. If you have the continue on, what you have is the following. Start, timeout, the timer keeps going. The flag is up, it's saying, you know, I did timeout, and then you will raise it again, timeout again. The physical analogy for this is the following. You say to the timer, count 50 million times. Counter times, counts million times, raises its hand the moment it reaches the 50 million, and then starts again. I'm going to count another 50 million. The hand is up. At any point, the CPU can come and do this. Right? As long as it does it within the second interval, I'm going to raise my hand again after another 50 million has happened. That's real time. There was no interaction. The time it takes for me to raise my hand again has nothing to do with how much time the CPU took to respond to my first time raising the hand. You with me? It's like having a person that you know they're going to raise their hand every 50 million times. If you don't respond to them within the first time, their hand is there, still there. Okay. This is real time, nothing to do with what the CPU is doing. So if you want to do audio or anything that has to do with real time events, this is the way to handle it. Now, I think that's a signal where time is up. So in time it is up. So I'll see you. I hope you get to enjoy a little bit of the weekend, long weekend, and I'll see you next week, Wednesday. We're going to finish the timer. Unfortunately, Thursday I'm not going to be here. I'll ask Mustafa whether he can come and give you a lecture on virus attacks using the stack.